Hello everyone and welcome to my channel. My name is Alessia and today we'll talk about the implementation and applications of quicksort. Quicksort is a sorting algorithm in which we pick a random element and partition the array such that all numbers that are less than the partitioning element come before all elements that are greater than it. The partitioning can be performed efficiently through a series of swaps. When we process a partition, we need the two key elements, the pivot, that in our case will be the rightmost element of the partition, and the position I of an element greater than the pivot, which initially is the position of the leftmost element minus 1. Let's take this unordered array and see how quicksort works. The first time we call the quicksort function, we have to process a partition that's equal to the whole array. Our pivot is 63, so let's now process the partition. The first element we process is 3, which is less than 63, so we increment I. Now, I corresponds to the position of 3, so the swap has no effect. Next, we process 82, which is greater than 63, so we move on. Here comes 15. It is less than 63, so we increment I, which now represents the position of 82. Therefore, we swap 15 with 82. We repeat this with 1, 40 and 37. After that, we swap the element at I plus 1, 82, with the pivot. As you can see, every number less than the pivot is positioned to its left, while on its right we find the numbers greater than it. Finally, we return the position of the pivot, I plus 1, and we repeat the process recursively for the left and right partition. We briefly explained how quicksort works, so let's now see what data structures we'll need. If we want to sort an array, we'll just need the array itself, since we'll order the array in place. Let's now write the function to perform quicksort. If the partition is valid, we find a pivot element such that the elements smaller than pivot are on the left and the elements greater than pivot are on the right. After that, we recursively call quicksort for the left and right partition. Next, let's write the function to find the partition's position. First, we choose the rightmost element as pivot, and then we define the pointer for elements greater than pivot. Now we traverse through all elements and compare each element with pivot. If an element smaller than pivot is found, we swap it with the greater element pointed by I. When we exit the cycle, we swap the pivot with the greater element specified by I, and then we return the position from where the partition is done. Now let's write a test class to check that our algorithm works correctly. We'll write two test functions, one to order the array from the initial example and one to order an array of characters. Let's test it. Perfect. Let's now move on to the time and space complexity analysis through big O notation. We'll start with space complexity analysis. As we saw before, quicksort performs every permutation in place, therefore no auxiliary structure is needed and we obtain a complexity of O of 1. Now, let's go through the time complexity analysis. In quicksort, we repeatedly partition the array and its subarrays around an element such that the array will eventually become sorted. On average, this gives us a runtime of O of n log n. However, as the partitioned element is not guaranteed to be the median or anywhere near the median, our sorting could be very slow. This is the reason for the O of n squared worst case runtime. Let's now list some of quicksort's applications. Quicksort is a great algorithm for commercial computing. It's often used for the purpose of sorting various data by name, date, price, and much more. Quicksort is also widely used for cache sorting because of its good locality of reference when used for arrays. And that's all for today. Thank you for watching. The complete code is available on GitHub, and if you enjoyed the video and want to support me, like the video and subscribe. Ciao!